Hello, everyone. Today I will present InverFill, a one-step inversion method for enhanced few-step diffusion in painting. Multi-step inpainting models like SDXL Inpainting have high quality, but require 20 to 50 denoising steps, making them too slow for real-time use. Few-step models are much faster. However, when we directly apply blended sampling to them, the results suffer from low-quality artifacts and poor harmonization. The root cause is that random Gaussian noise input is semantically unrelated to the masked image input. Multi-step models can gradually fix this mismatch over many denoising steps, but few-step models make large jumps and do not have enough steps to recover, hence leading to inconsistencies and artifacts. Therefore, initialization must be semantically aligned in few-step inpainting regime. Our key idea is, instead of starting from random noise, we use a semantically informed inverted noise from a one-step inversion network. With InverFill, the outputs blend seamlessly with the background and of high fidelity. Importantly, this adds at most 0.06 seconds of overhead on a single A100 GPU, practical for real-time applications. Our method makes 4 key contributions. First, InverFill creates semantically informed noise in one step. Second, reblending prevents information leakage during training. Third, Gaussian regularization keeps the noise latent close to the expected Gaussian distribution. Finally, our training is single-stage and real image-free, without requiring image mask text triplets. Our training pipeline has 4 main stages. First, data synthesis. Instead of using real image, frozen pre-trained generator G synthesizes a ground truth image latent. We then randomly sample a mask and apply it to create the masked image latent on the fly. Second, inversion. Our one-step inversion network F theta takes the masked image latent and predicts a noise latent ZT hat. Third, reblending. We replace the masked regions of the predicted noise with fresh Gaussian noise to create blended noise ZT hat prime. Finally, reconstruction. Generator G takes the blended noise and reconstructs the image. We apply losses in both the noise latents and the image latents for training. Training on masked images causes visible structures to leak into the masked noise latent. Without reblending, the inverted noise contains image-like patterns, deviates from Gaussian distribution, and the reconstruction collapses. The solution is straightforward. We keep the predicted noise in the unmasked regions and replace the masked regions with fresh Gaussian noise. With reblending, we prevent information leakage. As we can see, the inverted noise is more aligned to Gaussian. In implementation, this operation is applied in both training and inference. Even after reblending, the blended latent can still deviate from the Gaussian distribution expected by the diffusion model. The reason is that the newly added noise in the masked region may not match the original inverted noise background. Without Gaussian regularization, this mismatch causes poor reconstruction. The background is not preserved well, and the main objects lose fine details. So we introduce Gaussian regularization to make the blended latent more consistent and improve reconstruction quality. The idea is to enforce the first and second statistical moments, the mean and variance, of the blended noise latent to match those of standard Gaussian distribution in 0i. With the regularization, the background is well preserved and fine image details are faithfully restored. Let me summarize all our training objectives. The noise loss reconstructs the noise latent in the unmasked regions only, since the masked regions contain no meaningful information. The image loss ensures the reconstructed image latent matches the ground truth. The Gaussian regularization loss aligns the blended latent to the standard Gaussian distribution. We also use adversarial loss following LAD, where the frozen teacher model serves as a discriminator to improve visual quality. For evaluation, we test on BrushBench and Magic Brush. We use 4 metrics: image reward, HBSV2, aesthetic score, and clip similarity. We evaluate both DT-based SNA and UNet-based SDXL Turbo under 2-step and 4-step generation. Looking at the full table, InverFill improves every baseline across image reward, HBS, aesthetic score, and clip on both BrushBench and Magic Brush benchmarks. Notably, our few-step models at just 4 NFEs match or surpass specialized multi-step inpainting models that use 30 steps. Here are the qualitative comparisons. Each row shows the ground truth, mask, and outputs from different methods. Without InverFill, SNA Sprint and SDXL Turbo produce artifacts, color mismatch, and poor background harmonization. With InverFill, The same 2 to 4-step models generate results close to strong Inpainting baselines, including SDXL Inpainting at 30 steps and BrushNet at 4 steps.